Hello, everyone. We're going to discuss section 2.2, the evolution of atomic theory. Again, I'm going to go through your textbook for this instead of a separate PowerPoint, in part because I think your textbook, actually most textbooks go into a lot more detail than I think is necessarily important for these ideas. So we want to sort of scale it back a little bit, and I think it's easier to do that as we look at the textbook as opposed to in a separate PowerPoint. So let's start with the learning objectives. So number one, outline milestones in the development of modern atomic theory. Two, summarize and interpret the results of the experiments of Thomas, Millikan, and Rutherford. Three, describe three subatomic particles that compose atoms. And four, define isotopes and give examples for several elements. So I want to kind of preface this, and again, we're scaling this back somewhat. In terms of what we need to do, I don't care that you remember the specific names of the people that were involved in these experiments. It's more that you can associate, this experiment, why that experiment suggested the existence of one of these subatomic particles. And that's kind of the main thing I want you to get from this. You don't have to know them in detail, know the people's names, know the dates and things like that. So let's go ahead and get started. We talked in the previous section 2.1 about atomic theory, so the idea that things are made of atoms. So when that idea kind of took hold in the next 100 years, people were really into atoms and elements as being really important. So the discovery of elements was kind of a big deal, and the idea that there could be something smaller than an atom was very kind of controversial and not thought of as even possible, because everyone had latched onto the atom as being kind of the smallest thing. So it turned out, though, that there were some experimental results that could not be explained with anything other than something smaller than an atom. So those involved something called a cathode ray tube. We're showing an example of one here. Another example of a cathode ray tube, and we'll have one that we'll look at in lab at a later time. But if you have seen an older television that's not a flat screen but kind of a bigger box, those are also cathode ray tubes. And basically, we're showing kind of how they work. So there is a stream of, let's actually back up, not how they work today, but kind of how their discovery was made. So what happened was a metal was placed in this vacuum tube, and electricity was passed through through the system. So you've got two parts of the connection here, and regardless of what metal was used, what they saw was that when they did this, there was this beam of particles, or beam of something. I should start by saying just beam of something that was coming off of this, and it was a colored thing, and they could see it when they did this. And one of the experiments they did is they put a magnet around this tube, and what they saw with that is that the particles bend when they do that, or I should say whatever this was, this ray of things started to bend. And I'm backtracking to say ray because maybe it's a form of light they're seeing, but if it bends, it turns out in physics that you can't, you have to have basically a mass in order for something to bend like that. So they're bending it. Okay, so it looks like maybe something's, there's a form of matter there that they're able to bend. And what they saw is, regardless of what they put here, as long as they had a metal, they tried different metals, they got the same thing every time. And what that is suggesting is that there is something inside of that that's kind of coming out of it. And whatever that is, it has a mass. And if something is coming out of an element that has a mass, and the element is made out of atoms, that's telling you that there's something inside the atom that's coming out of it as you do this experiment. So that was kind of remarkable and hard to explain without suggesting that there was something inside of those elements. And so that's essentially what they did. They had to come up with, okay, there's something inside of these elements. We now call this an electron. Okay, so an electron has a negative charge. The idea that it has a negative charge is basically based on how the magnet bends it. We don't need to get into the details of that right now, but that's the idea. A negative charge is related to the way in which it's bent by the magnet. And that whole idea of charge being positive or negative, it's essentially, it's a convention that was decided at some point in time. And if you don't like it, you can blame Benjamin Franklin, is what I always say. Because sometimes when we look at charges, would make more sense the other way around. But electrons, we say, have a negative charge, and they have a mass. And it turns out that the mass that they have is about 1,000 times less than that of an atom, depending, of course, on which atom you have. That was the discovery, basically, of electrons, were these cathode ray tube experiments. So that was one idea. So late 1800s. So within about a decade or two, more people were doing experiments on this idea of electrons. So they knew, okay, we have these electrons. So how big are these things anyway? So the experiment was the oil drop experiment. And so just kind of remember, oil drop experiment is what goes with what we'll be talking about next. So what happened is they sprayed oil into this container, and by varying the charges, they could look at how fast these drops are falling, and in this region, and maybe the oil drop has 1 electron, maybe it has 2, maybe it has 3, maybe it has 50. They don't necessarily know, but by looking at this and looking at the charges, they were able to find, okay, what's the smallest possible common ratio? The idea being there is some finite number of electrons on each of these oil droplets. We're going to figure out how much that is. Now, to actually do this experiment, there's a lot of math and physics we don't know that we're not going to get into, and it's really tedious as well. To make this sort of a thing work. But the idea was, okay, we're going to figure out just how small these electrons are. They did know, based on this experiment, what the charge of the electron was. And so if they knew the charge, they could find a mass to charge ratio, and from there figure out the mass. So from that experiment, they found out the mass of an electron was very, very small. So the number here is 9.1 times 10 to the negative 31 kilograms. You don't have to memorize that number. It's a very small number. But essentially the idea there was, this experiment led to, we know there's electrons and we know they have a mass and we know what that mass is. So they were able to come up with that. From that information, there were some models created for what people thought the atom looked like. So now they knew atoms had things inside them, like electrons. And so what was an atom? What was an atom like? And the model that most chemistry books talk about is what's often called the plum pudding model. And I have never actually had a plum pudding. I don't even know if I would recognize one. Maybe this is a plum pudding. So I think of it as a food that I know about, which is a watermelon. And the idea is you have these clumps of things that are electrons within the larger thing. So think of a watermelon with seeds in it, and each of those seeds is an electron. And then the rest of it is a positive charge, um, because we know overall the atom has a neutral charge. So if the overall thing with the neutral charge has some negative charges, then it also has to have some positive charge. So that's the idea of um, the plum pudding model. Um, and then another model was basically that it's sort of like Saturn, where you have these electrons in a ring and then some positive charge sort of in the center. This one actually, as we'll see, is a bit closer to reality than this one. Neither one of them is correct, but this one was a bit closer. And I think most textbooks go with this one, probably in part because um, just the contrast between our modern understanding is bigger, whereas there was actually a better model at the time that someone else had come up with. Okay, so the next experiment, again, you don't have to remember all these people and all of the details, just kind of associate each experiment with, well, what does that tell us about atoms? Involved alpha particles, and we don't have to know all the details of alpha particles right now. We'll get into that next semester. But essentially, alpha particles are um, they have a they're fairly massive. They're much bigger than electrons, and they have by much bigger I mean like thousands of times bigger, and they have a positive charge. So someone thought, well, why don't we shoot some alpha particles at a substance and see what happens? And I guess there's this quote that from the person that did this. It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So basically, I guess a 15-inch shell is sort of like some kind of a cannonball fired at a Kleenex and it bounces back at you. That would be pretty remarkable. And based on the plum pudding model, that's what they would have expected, that it would bounce, that it would not bounce back, that it would basically shred that Kleenex. But that's not what happened. It bounced back. So that was telling them that their model, the plum pudding model, was not working very well. Which is, the way science works, right? Our models don't work, so we come up with better ones. So based on this model, so most of them went right through. Okay, so that wasn't unexpected, but some of them would bounce, maybe off to the side, or some of them would even bounce backwards. So a significant deflection. So again, doing lots of complicated math that we are not going to do. What they found from this result was the only I guess the best explanation for what they saw, that most of the particles went straight through, was that most of the atom is empty. There's nothing there inside of atoms. But when there is something, it's very, very massive. So a small, relatively heavy, positively charged body must be at the center of each atom. So we call that the nucleus. So within the atom, this new model is saying there is a very dense, very massive thing with a positive charge at the middle. And then there's electrons that are not as massive. And we don't necessarily know what they're doing right now. But they're not doing this, right? Because it turns out for the watermelon, that model didn't work. You actually have something very dense and then this very nebulous thing around it with a negative charge. So those are the experiments that led to our modern understanding of what's inside an atom. And in the next module, we'll get into more detail on that.